have a good deep sleep for the weekend, right, going forward. So without further ado, let's start on the deep learning applications. Currently, you see how many is it has reached the stage. For example, we can see deepfake, right? You can read up more about it, where it can generate sort of a replication of another person on the main body using generative adversarial networks. So that's one very popular use case. Or you can generate musics. So we are in the generation phase with deep learning technologies. On the right, you can see more traditional solutions, such as captions, where we can take an image and get a summary of the image, right? So that's also the ability of generating and transforming and converting data from image to text, text to image, speech to text, etc. So what you can see, deep learning, the applications is really centered on the more advanced ways of playing with all the unstructured data you get around you, which can be 80% of it because your senses, for example, your sound, your taste buds, your hearings, speech that you speak on a daily basis are all being able to analyze and process. Even in the field of robotics, right? You can apply DL in allowing robots to learn the actions that are rewarding over time. Okay, so beyond generation, we can see there are other kinds of applications. Is very common that you might have heard of Tesla, which is object detection, right? As you can see on object detection, what really happens is that it can even go on real time, such as video recognition, right? As the car drives or any vehicles that drives, it reads in image, okay, cutting videos into frames, and then detecting the bounding boxes for every object you see with a confidence score, right? You can see that, for example, the keyboard each have a 99%, 96% kind of strength that you will measure in order to sort of know what is the accuracy that you're trying to predict for persons, for car, for traffic lights, right? And on the right is a bit of more of even point-to-point vector kind of predictions, post estimation. Right? So after you see the differences in the applications, how is it different from machine learning, right? Which you have more or less covered probably previously, or you might have heard of it somewhat. So in the field of deep learning, you can see quite commonly as a very niche subset of machine learning. It does predominantly focus on an area of algorithms, which is what we call the very infamous neural networks, right? Where you layer multiple neurons and multiple layers to try to extract features of the data and learn it. Beyond machine learning, there's other fields, right, which you have more or less covered, things like linear regressions, classification, logistic regressions, random forest tree models, right? Even stochastic kind of support vector kind of models as well. So all these are the field of machine learning, right? And beyond that, AI is where deep learning sometimes just embed into a tool. So a lot of times you see deep learning services, right? They don't just exist as a black box. They are usually in products, right? Like as mentioned just now, even if you look at AWS, deep racers, okay, a lot of deep composers, they are already deep learning services that are built on top of products. So that's how it goes. Another more important way to see the difference is, for example, the extraction of the feature and then doing classification. So if you look at machine learning, right, what it does is that you will have a step where you have to get the data, right? Then you have to clean it, process it, whatever, engineer features. So that is done in the pipeline method, right? Then after that, your algorithm comes in, and then you try to predict whether it's a car or not a car, for example. In the same kind of problem, car or not a car, the data for machine learning could be in terms of the tabular data, quite a structured data. Deep learning could be image, right? And then the key is that in the neural network itself, right, you do not see that the process is being split. The process goes concurrent, right? You extract the features as the networks progress. On top of that, you do your predictions, okay? You figure out which features in the image, for example, are strong and not. Okay, so that will be more later when we look at a specific family of neural networks, which is the convolutional, okay, layers, right? Now, where did deep learning begin? So for you to really appreciate an able to see why deep learning as a neural network, right, sounds very basic. But as you build that algorithm, there's a lot of components to it. It's because it replicates a lot from the biology perspective, such that when informations are being passed from your, let's say, your eyesight, right? If you are looking at me right now, the image that you are receiving goes into your eyeballs, obviously. Then the eyeball sends a neuron. Your brain is not connected directly to your eyeballs, right? There's almost a forehead distance away, right? So it has to send the data in, correct? And then it process it, okay, and pass it forward, all right? So if you imagine your entire body is filled with neurons, one cell after one cell, to overcome each cell, right, there is this thing called the synapse here, right? Correct? We won't go so deep into these concepts per se, but more of appreciating why and how neural network begins. Right? So for the neurons to be able to send image and data from, say, neuron 1 to neuron 2, and even to neuron 3 all the way to your brain, right? You must be able to pass through a kind of energy level, right? It must have enough energy, and that is where activation functions comes in neural network. So this is a very common term in our development of a network, where we have to take care of what are the activations that we are going to give to the data. Is it going to be linear, non-linear kinds of activation? Does the data have enough output to sort of overcome the threshold to pass it forward? So that is where the relationship with your biological brain comes in very handy. Okay. Now, so as I just explained, right, if the data has to come in from the image that you are looking at right now, the videos, the slides that you can see goes in your eyeballs, that's almost like your input layer, right? So data has to be coming in, correct? As the data goes in, it passes through many neurons, right? So-called layers of neurons or nodes, okay, or perceptrons, the more scientific words for it, right? And then all the way finally to the outputs where you probably do a classification per se, and there is class 1, class 2, class 3. It could refer to dog, cat, or bird, whatever, right? So that's how that neural network was built, right? And for the data to be going from one end to one end, it must, as I explained, have enough strength to overcome certain threshold, okay? And that is determined by the activation function, right? Okay. So neural networks are, in essence, loosely sort of modeled after a brain. It has evolved to as complex as a brain can get, right? With many forms of layers, many forms of interesting transformations of the data that you can add to the network. Okay, so the key today is that in many state-of-the-art, so-called SOTA models that you see out in the market, they are very, very huge layers. In fact, one popular one, for example, in image computer vision, right? ResNet 101 is about 100 plus layer, right? So 101 to be more specific, right? So that's where you see it has reached a lot of developments into fine-tuning it to learn a large amount of data. The corpus of image that you process could be in the millions range. So that comes in terms of also computational resource and other constraints to take note. But at least we know now it's feasible. It's just whether do you have the resource to do so. Okay, let's break down the network then in more specific terms. So input layer, as you do, you are just passing the data into the hidden nodes, the neurons, right? The hidden layer can go basically all the way up. It could really even just from input to output, but that's very rare, right? And then they are sort of, we call neural network, usually you hear is a black box because it doesn't really work directly with any external environment. The output labels, the output results get sent as APIs or inference endpoint, right, where people can access. But within the hidden layer, they do a lot of computations and calculations in order to transform the information from input to output. All right, and finally, the output layer is where, as explained, you just get your classes or get your regression, if it's a regression, your values, and you make a predictions, right? So the key is there are really two things in the network as we conclude beyond just the activation function, right? Is where we have the number of hidden layers and the number of neurons that you can vary, right? So One thing to note that if you increase the layers, what you are trying to do is, for example, right, increasing what we call abstract representation. Because the data coming in, as you see in the network, could be fixed, the original data size, right? But as you transform it with increased number of layers, you are doing a lot of mathematical change to it, right? You can make it to a polynomial or even a higher dimensions, or in most of the time in convolutional layers, you are trying to reduce the dimensions features, right? Secondly, if you increase the neurons, so layers is, for example, 1 layer, 2 layer, 3 layers, right? And go all the way to say n. Neurons is within 1 layer, you can have 1 neuron, 2 neurons, all the way to m neurons, right? So if you increase neurons, imagine the input layer coming in, right? If you just reverse back to the previous, if we simply increase these neurons to say ×2, okay, in this layer we have another 5, so that's 10. With the same data that comes in, you are splitting the data or extracting smaller features of the image, right? So hence that would be the most straightforward appreciation of when you increase neuron, what will be the outcomes of that. All right. Is there any questions? Feel free to just put in the chat or whatsoever, and we can have a discussion. So what you can see, as mentioned on the right, some kinds of common state-of-the-art models today. These are all mainly the suite of computer vision kind of CNN networks. They can go up to many layers, and in between you're extracting, doing a lot of transformations, right? And that we can do on the data itself. Okay. There is a rule of thumb. So if you are building your own bespoke custom model yourself, generally your hidden neurons, this is just advice, right? Commonly in the market. It doesn't mean you have to follow. So a lot of times when we train neural network, right? If you have some experience, you'll realize actually neural network overfits the data a lot due to its complexity and its ability to extract features to a very granular level, right? So it tends to overfit, meaning you learn the data too well and you can't really predict uncertain future. So what you might want to do instead is to reverse that. You want to deprioritize your learning, right, in the training, and be able to predict sort of generalize in the future, right? So you actually want less hidden neurons. The moral of story is, as far as possible, every incremental layers of neurons you have has to be proportionate to the number of data you are dealing with. No doubt the state-of-the-art models are very huge layers. That's also because if you look at like ImageNet, the kind of data size they have is in millions range, right? And thousands of clusters. If you're not dealing with that size of the problem, whether it's for the competition or in real life, you probably don't need to build your own bespoke model that has so many layers. Alternatively, is you take pre-trained models and you leverage on its learnings and improve just to customize on your current data, right? So that's is a quick brief, as brief as and as sufficiently deep, I hope, into neural networks, right? In how it's being operated and what are some basic fundamental building blocks to it. So imagine it like a Lego, right? Just build it from a step up, right? Small blocks of neurons, small blocks of layers, and incrementally add on it, right? So that's the key. Now, then what is actually happening inside the calculations, right? So this goes to a concept that actually probably most of you might already have experience with it. So it's just as simple as a linear regression, right? Or more other ways of calling it is like linear algebra, etc. So for example, in a simple math, how do you solve this, right? So father is 22, your 10 years later, your father will be twice. So that's enough. All right, so let's assume you are is an x, right? So that's the son, the father is basically x plus 22. 10 years later, it will be x plus 32, right? Okay, then this will be x plus 10, right? Okay, so this actually should be y, right? Let's make it y, x plus 32, right? Correct? And 2 times this x plus 10 is actually x plus 32. So 2x plus 20 is x plus 32. So actually x is basically 12. So in essence, you can really solve for x, right? And if there's a y, you will also be able to solve for y, right? What if there is more, right? Features, so x, y, and z. So that's basically, if you do the same process of calculations, right, and solving the values, okay, 3, 2, and -1 will be sort of the data point, right? You will be able to get it. right? The weights, if X, Y, and Z are representing weights. So that goes into how neural networks really work, right? In this algorithm, is trying to solve the weights of all the multiple data points. So you can imagine doing the same as just now, right? Doing an equation of additions, okay, with the multiplied weights and the value itself. So each neuron, okay, in the hidden layer, let's say hidden layer 1, you have the weights of 1, 1, right? 1, 2, and you multiply with x1, x2. So all the way you can have xm, you will have w1m, for example, right? And you aggregate them up, you add them up. Right? So that simply is the first, okay, that you will be doing, right? Then plus w12 plus x2, and then you all the way, right? Do w1m by xm, right? So you can see that in just one neuron, you have this series of equations. Now, if you understand a very basic, if you have one unknown, you need one equation, right? If you have n unknowns, you need n equations to solve n unknowns, right? In order to be able to deduce. Otherwise, a few weights will be dependent on other weights, which hard to leads to a conclusion, right? So you can see that the hidden layer, each of them are solving the same few permutations of the data, and they hope to reach a lowest error that they hope to achieve at the end by optimizing the weights. So it's like finding a combination of weights for the data at every single layer that can help to reduce the loss. And this is sort of feed forward, right? Of course, so you are sending the data forward and you are learning the weights. Okay, then after that, finally, when you predict, say, your output, you will try to see whether there's a gap in the error, then you will, that propagates. So going backwards to optimize the weights again, so that's how it will work, right? So a neural network will work forwards and also will be able to work backwards. So working forward, you can see like when you learn something like now, when you learn something probably new that you might not have watched, known before, you have to absorb and try to assimilate the new knowledge, right? But then you will try to do a reflection after that. So imagine after today, you go to do a reflection, you realize that there are gaps in your learning. So the error, okay, minus the predicted is high, and you want to lower it, right? You have to go back and change the weights. If you change the weights, you will have to change the layer errors, and then you have to change the weights again, right? Until you reach the input. So that's how backpropagates works, okay? So when you increase the neurons, you in essence solve the linear combinations of the data features. Dimensionality complexity means a normal machine learning models probably, especially unless you are dealing like support vector machines where kernel size can be polynomial, etc. Most of the times the dimension is an issue, right? You don't want to deal with a lot of features and increase the complexity of problem. But neural network is best suited for this kind of high dimensional problems. Last but not least, there's also a type of problems that is best solved by neural network is the kind where it's non-linear problems, right? It's like things don't really happen in a linear relationship. A lot of things in this way you realize don't really happen in a relationship. For example, your learning hours and your grades, right? Normally your grades and learning hours is not a linear line, right? It cannot be going infinite, right? So what happens is generally you might have a sharp rise and then you start to slow down, right? So actually every incremental may not be good, may not be that worth extra time. Or you can go very slow, then suddenly you're a late gamer, right? So at the end, suddenly you increase your learning. So for whether it's the blue or the orange line, it is non-linear relationship and you are able to solve by the neural network, which is more suited for it. So now if you see how two neurons are working together, then you can see how it probably relates to one another. So if you have many X, in this image you see only 3, but let's imagine 3 as the start. You can obviously increase that, right? So there will be respective weights, right? So 1, 1, 1, 2, etc. You see that each neuron is calculating, okay, their respective weights, right? 11, 12, 13. Okay, and by a bias node. So a bias node is set usually as default as 0 or a 1, depending on whether you want to give some bias to the data. Okay, and also the weights of the bias will be learned by the network itself. Okay, but the bias value is usually set as a parameter by the algo, the engineer, right? So if the features is x1, it remains the same, but the weights, okay, and you can see the parameters here, there are 6 which are trying to tune and trying to change. The next layer, finally, the A3 depends on sort of W31 and W32, right? Depends on A1 and A2, which then depends on W11 and W21. So if you change the front layer weights, you have to change the next layer weights as well, right? Vice versa if you reverse it. Okay, so that is how finally after you do the regressional outputs, right? You have to pass it into an activation function. An activation function is basically like any trigonometry functions, right? Your sine functions, your cosines, okay, are very straightforward functions, right? For those who are not even aware of what's a sine function, it's basically those kind of function where you have repetitive cycles, like a sound wave, right? Or any waves data that you see, right? Like the heartbeat, right? It's in pulses. So those kind of functions are modeled usually sine graphs, cosine, or even other kinds of exponential functions, right? Okay. So hence the non-linearity is really achieved by the activation function. So after I have all the linear combinations, I will join together as into a final output, right? Passed by the activation function, just like the neurons of the brain that I've illustrated just now. Looking forward, in your neural network, right, you could change the activation functions with these few options. There's a range for you to change. This might or might not be very consequential. Usually people start off with like relook, okay, which is a linear kind of activation, right, which you can see here, right? And it's basically the lowest you can get is 0. The highest you can get is infinite, because it goes all the way out. The reason why this might not be good is if you think logically, you wouldn't want infinite values, right? It can explode the values by a large amount, right? So in math, right, a larger number have more priority in essence, right? 10 is appeared to the machine to be more important than 1. So at the end of the day, actually, when you are doing predictions like classification, right, is this an image, a dog, or cat? It ends off with either sigma or the softmax, which is regulating it between 0 and 1. So no matter what's the final calculations in all the additions, right, as mentioned that you saw just now, right, all the weights are multiplied with the data and then you are adding them up. You will pass into this function and it will comes up between 0 to 1. So regardless what was the regression outputs, in that case, it is able to control the outputs of the network itself as it passes the data forward. So what you can sense to a certain extent is as this network goes more and more complex, right, it's harder to explain what's happening in the network itself. Right. So although it seems as straightforward as a linear combinations of features, you're adding everything up, but trying to deduce what actually transform or happen within the layers of neurons and calculations is not that straightforward. Right? So that is the interesting thing about deep learning. Okay. So well, you know how it operates, there must be an objective that it works, right? So that's where you have to take note of also changing this thing called a loss function. Right? So a loss function is essentially calculating the errors from the prediction, right? Quite straightforward. If I predict it's a cat and it's not a cat, I'm 100% wrong, right? If it's a dog and it's a dog, then I'm 100% right, right? So that's just accuracy, right? Okay. So I take the true output minus the predicted output, and I have this j, which represents a function, okay? It's just any function that you can imagine, okay, that can calculate a loss. The mathematical component of that is not necessary for this very brief and sufficiently deep introduction, right? But just appreciate that the goal is always to reduce this value. And to reduce this value, as what you will have to do is to change the weights as mentioned just now, right? Okay. So let's imagine that in a graph, there is all the combinations of weights, right? In the network itself, there are so many different weights that you can get. So I will have to have a loss calculations, right? So in this loss calculation, obviously the higher you are, the more errors you make. We want the lowest possible in every algorithm. The universal lowest should be 0, right? You can't possibly go unlikely lower than 0 most of the time in accuracy. Loss, right? So let's say in this graph, you can see this is the lower point. This is the best point, okay, in this graph, right? So you want these weights, which can be from W1 all the way to W n, okay, for the network, you want it to be this set of weights that give you this loss. As the model learns, right, it could be at any point in this graph, but the model needs to know that it must reach this goal, right? So it's actually trying to reduce and go down to this goal, right? So as it's going down to this goal, you can tell that it's actually a gradient, right? So-called a rate of change, right? Or in mathematical terms, a derivative. Basically, is how fast this red color ball is going all the way down the green color ball, right? So if you can reduce it at the fastest rate, the key mechanism to do that is gradient descent, right? So gradient descent will help you to reduce the loss by adjusting the weight, right? At this red color dot, there's another set of weights, right? So I want to change that weights to get to this green point. And each time I change the weights, I can make incremental steps to reach to the green point, right? And that in the sense, once I reach here, the gradient should be 0, right? Whereas here the gradients are, if you see the slope, it should be decreasing very drastically and starts slowing down, right? That's why it's called descent, okay? So that is the gradient descent itself. But then when we say we want to change the weights, what affects how much is the weights being changed, right? To reduce the loss. That's where important information like learning rate comes later, right? So as the gradient descent solves, right, it is trying to reduce the loss function and change the weight, right? How much to change each weight is by this thing called the learning rate, right? So the learning rate is the goal, okay, of trying to adapt the weights. So for example, if weight 1 is say 2, if I want to change weight 1, correct, I need to add the learning rate multiplied by some factors, okay? So this is my learning rate, right? Okay, so this learning rate actually is determined and set by the engineer. So as an engineer yourself or a scientist, you set this learning rate. You can do a dynamic learning rate today in a neural network, which means the learning rate will start to change after it learns in a model that it can start to reduce the learning rate, okay? So reducing the learning rate helps you to achieve the minimum a lot. Later I will explain in deeper terms, right? So as you can see, for every parameter of the weights, okay, the loss functions, you change the weights, let's assume that the loss function decrease, your gradient is actually dropping, right? So that's the key goal of it. All right, if you just draw a straight line and tangent to every point in the graph, you should see that the gradient here should be decreasing, right? Okay. It is negative, right? So in essence, it should be increasing. So that's the key, okay? But the absolute values is actually decreasing. Now, the mathematics is not that critical for you to appreciate, but if you are interested and you're the brave kinds, you can figure out from this math, okay? But as you can see, we are just calculating how fast it reduced to the optimal goal, right? So this is the best point you want, and you are changing that with the weight itself. Now, not everything appears as a nice curve, right? Just to increase the complexity is that, remember your neural networks have tons of weights, right? So most of the time is the function, right? The gradient descent doesn't operate on the left, which is such a nice curve. It can get very complex. The topology or the shape of the network can be pretty complex. So you are just, let's illustrate with 2 of the weights, right? You are still trying to decrease to the blue zone, which is sort of lower than the red zone, right? In a 3D space. So that's where higher dimension and complexity happens. What happens is that one concept that in the neural network is sort of blind. It doesn't remember really where it was previously. Each time you run one episode of training, right, you sort of restart or sort of start from a random point again and try to reach this convergence. So there can be a chance where you don't really reach the lowest point. It's not that, it's not a guarantee, right? But of course, as a scientist and engineer, your role is to make sure that it does reach the minimum point. Okay, when it's minimum point at this point, mathematically you call it converge because both left and right is reaching the same point, right? Otherwise, it also because you are minimizing the errors, right? So this learning rate that are trying to change, how does it affect the entire model is this, right? So it determines how the weights is updated, as mentioned. Then what is the challenge if it's too big or too small? If it's very small, you will have a higher chance to reach the lowest point, right? It's like, for example, you want to study for a test, right, or your exam. you spend 20 hours on it, you are likely to do better. Okay, assuming everything holds constant with the general knowledge that more outward leads to success. Let's assume this theory, and you realize that you slowly remember everything, take more days to remember every chapter, you will get to the lowest point with higher chance. It's not like guarantee also. There's still no guarantees anywhere, right? Anyway, right? But at least your chance is higher. Now, if you are another kind of student that just learn very quickly, learning rate, right? So if you learn very quickly, right, you put a very large learning rate, what happens is you just jump around. So you can be very lucky that imagine it's not this black line, right? You can be very lucky that the next time you learn, you are here already. But more than often or not, the probability, the chance of you reaching the red color minimum point is actually very low. Likely you are going to miss the lowest area, but you learn fast, right? So you can complete training, for example, people takes 10 hours, you can complete in 2 hours, right? If you set a very large memory. Because it doesn't process the data and that much, right? It doesn't update the weights. Remember, it's updating the weights. If my learning rate is 0.0001, you can think that of it like the weights is changed by every 0.001, which is very little, right? So each small change of weights, you're going to check whether it's going to improve your error. That takes time, right? But if your learning rate is like 0.1, which is much higher by a factor of 1,000, right? You are going to obviously learn very fast, right? Each time your weight change is 11.1 to 11.2, for example, just for example. So you can realize that you don't have so much permutations to change, right? Or combinations of weights to analyze. So the learning is faster, right? So that really sums up a few key things, right? If you see hidden layers, neurons that you have to decide how many, the learning rate you have to decide what number, the activation function you decide what number. Gradient descent is a concept that I've shared, but actually the way to decide on that is the optimizer function, right? That one can be added, which is it just combines everything else, right? Stochastic gradient descent. Okay, every other optimizer is sort of combined into Adam. So all these are what you can change to and build that model of the network, right? Which I will show you the code more or less later. Right? Of course, if you use APIs like Keras and TensorFlow, Keras especially, right? They abstract a lot of these fundamental tuning, right, or customization of the algorithm. But still, I think even Keras, there's some steps you have to do, right? Which is to set the number of layers, to set the learning rate, to set the optimizer, to feed the data, right? So those are still the same things that you have to do for your network. Okay. On the training perspective, right? Just take note that imagine I have 1,000 image, right? For me to finish learning 1,000 image, that's called one episode, right? So usually neural network like computer vision problem, you run 5 episodes. You should be able to see some change and impact. And then you can decide whether you want to relearn and train another 5 times. Okay. Next concept will be more of iterations, right? So it's like you can see in one episode, I can break my 1,000 data into batch, right? So batch is like 10 image per batch, right? So 10, 10, 10, so 70, right? Okay, or 700, each batch is 100 image, okay? So in essence, you see that I can have many epochs, which is the number of episodes I learn 1,000 data, right? So if let's say this is one episode all the way to 10, I will learn 1,000 data 10 times. But each time I learn for the first time, I may be splitting into like 7 packets of data, right? Take 1,000, say, divide by 7. Or makes it easier, right? Make 700 divided by 7. So each one is only 100 image. So actually what is sent through the network, each batch, right, is 100. That is called the batch size, right? So this is something that you also can change, right? To decide how you turn. All these will be fed into what we call the hyperparameters, right? Okay, which are very fundamental to the neural network learning, all right? And that is, as mentioned, how much for each springs to cover. So the iteration is dividing the episodes and batch size. Okay, multiplying them, you get the dividing the episodes with the batch size, you get the iteration. Okay, so that is how you essentially do the differences in training. All right. Okay, so without next. So actually, there's a website that can help you to more or less get more comfortable in neural network. You can actually take a look and see what are the things it computes. Okay, and Yeah, I just do a quick share on the Zoom chat so that you guys might be able to see. So you can come here, right? Okay, this is by TensorFlow, okay, which is pretty good to start for a network following a convolutional, right? So let's imagine you have this data that you want and you are trying to classify, right? So you can really start training, right? So you can see it's trying to learn and group the data up, right? This is the number of episodes you can see, right? So basically the data is being learned like 300 times. And of course, it can keep increasing, right? Okay. Then imagine you increase the learning rate to this, right? And I restart to, hey, let's say 10. So clearly you see that it's not learning because the learning rate is too high, right? Okay, so it's jumping around the entire loss function. If you reset it to this, which is the lowest value of the learning rate, right? Okay, you can take a while, you can see that it's basically very slow. I'm not sure if you can see there's changes. You should be able to see that the gradients of the segmentation is trying to change, but it's very slow. It's like 600, right? So these are the things that affects the learning of the neural network. All right. So a good one would be say 0.01. Then you can see this is it. What you can see is that the loss is also reducing. Okay. And it's trying to see if it can go. So you can see that there is a lowest limit of loss that's possible for this data. And this should be the best segmentation. All right. So that should be it. As illustrated just now, there are various activation functions. For these two per se, you can't really see the effect so clearly, right? So, but you can illustrate from the name of the activation function, it does different change to the data as mentioned, right? Sigma will be 0 to 1 range of bounds. Linear is clearly basically the higher your x, the higher your y, right? Okay, the rest are like your parameters, regularization, okay, to affect for the penalty for the bias, right? I probably won't go so deep into it. Feel free to research more if you're interested. Okay, the batch size is basically 10 in this case, right? So if you reduce it, it will take slightly slower, right? Okay, so that should be how it's looking at, okay? Or you can increase it, right? Which is 30, right? Okay, so you learn fast again, but it's not that comfortable in terms of finding the true value. So it actually takes longer if you realize, right, for batch size study. Because each time 30 image is sent in the network, it doesn't fully extract the or compare the image network. So you need it to run more episodes if you have higher batch size. Okay, so these are basically some change of every single thing to the network changes how it learns. Okay, you can increase your layers, okay, and see what happens, okay, or you can increase the neurons to see what happens. Okay, and more importantly, if you see, right, just now my network was actually very simple. Now that I've increased the layers, increased the neurons, will it guarantee a good result? The answer is no. So it's not that we must always expand on the layers or expand on the neurons. This is more important if you are building your own bespoke models, right? If you are not building your own bespoke models, then this might be less of a concern. So the Occam's rule, right, is a rule that we always say the simpler the better. So don't necessarily have to have so many layers and also not necessarily have so many neurons, okay? So you do have to experiment. The very key difference between deep learning and machine learning engineering is that you experiment much more in deep learning, right? It's like a playground, right? As the name of this website goes. You play around with all the different combinations and features to see what happens and the best. All right. So that is basically how essentially a neural network works. Okay. So in summary, you can see that there are many moving parts. All parts are interrelated, right? Experimentation helps computational limitations actually still exist. So this is quite a pertinent problem. So if you use like SageMaker, all of these, there are different instances that are running at higher compute, which may help definitely. Okay, or you figure out how to use things like graphical processing unit, GPUs, or even tensor processing unit. Now, going forward, you will realize that what I've shown was only a very brief first introduction to neural network. On the left, right, on the right, you see that there are two main class that probably in this session we will go quickly on. One is the CNN, standing for Convolutional Neural Network. Best use case ever is always to deal with image kind of data. So this image data just simply goes in and finally predict what classes it is. So there are many different layers. What you saw just now in our discussion was a simpler layers where we do additions, okay, and weights calculations, right? That is the fundamentals really. Now it's really types of layers that do interesting computation, right? The other kind of the family, which probably go through in another sessions, will be RNN, right? Recurrent neural network. It does mainly with sequence data, okay? CNN does with a static image data. It's one of the batch, right? So that's the key difference between the two. All right. Now, how did computer vision begin? Right? Let's think of it. So if you deal with tabular data a lot of times, you should know rows and columns, right? It's a table, right? So let's see, do you think that these two are the same, right? The one on top, the 1D and the 2D. So imagine this image has been cut. We cut this image into size, into strips, right? And each strip is layered. You add to get this, so sort of you concatenate the string. Okay, they are the same actually. They are the same. All right. Now, increase the challenge. Okay, these two the same, right? Now you take two image A and B, if there is, and you do the same process, right? Cutting the image into slice and putting the, okay? Why? Because this kind of data, right? Imagine a simple machine learning model supposedly should be able to learn this quite well. It's just tons of columns and tons of rows. Basically, the rows and columns may not even mean anything because image, right? You cut it and paste it side by side. It sort of loses the image understanding, right? The answer is actually they are not the same, but you cannot tell. Okay? If your eyes is very sharp, you probably can, but hardly you are able to see a very strong difference, right? So answer is actually they are not. And one very difference is the nose is here and the dot. So once you cut the image into strips and you stack them side by side, right? You couldn't really tell, right? If you do that kind of learning. So that is why computer vision in convolutional CNN networks comes in, right? It's because CNN is built to keep this sort of orientation of the image as much as more or less fixed. It sort of aggregate features in this image, right? Imagine trying to learn this image by a machine. How you learn that this was a dog is basically trained by your brain, which you cannot explain, right? But how a machine has to learn this to be a dog, the machine has to cut this image, okay, and into like grids. The smaller, the more features you extract, right? Remember neurons, and each features are being aggregated together. All right. So that's why CNN is the model that helps it to do that, right? Aggregating it without losing that spatial nature of an image. Okay. So it's no longer 2D, okay, it's sort of 3D, let's say 28 by 28. It goes through a convolutional layer, okay? What is a convolution layer? It's different from just now the simpler addition of weights, right? This is a matrix multiplication already, okay? Pooling of the layers, okay, aggregating the maximum features until finally you reach into a linear, fully connected layers, right? Which leads to 9 classes in this case. This is actually a very famous numbers recognition, right? Digit recognition problem, okay, of handwriting. So without further ado, if there's no big issue or question, let's look at convolution layers. So as you can see on the left, right, where the matrix is actually moving, what a convolution layer is it takes a yellow box, as you can tell, okay, and move along the image, right? As it moves along the image, right, it's doing what we call a dot product or matrix operation, right? You're just taking, say, 1 times 1 is 1. Okay, let's fix it. Okay, so let's look at the last one first. Okay, so you see that 1 times 1 is basically 1 times 1 is plus 1 times 1 plus 1 times 1. So that's actually 4, right? The last one should be 4, right? So that's how you actually do a matrix multiplication. All right, so you can see that this, and if you take 1 times 1 is actually 1, 1 times 0 is 0, 1 times 1 is 1 again, 1 times 0 is 0, 1 times 1 is 1 again, 1 times 1 is 1 again, 0, 0, 0. So actually, that's why you get 4. okay, for those that are not aware, okay? Or let's make it easier, right? Okay, let's look at this grid first. So it's basically 1, 1, 1. The rest are all zeros, right? All 0 times 1 is 0. So that's why it's 3. So actually, that's essentially what you're doing. If you move this kernel into the full image, this is just 5 by 5, right? Imagine 28 by 28, okay, or 128 by 128. You can see the complexity of this. What is important to know is that while the network is aggregating the features, okay, it doesn't lose the spatial orientation, which means that it's trying to say that originally the features here is of, say, a weight of 4, okay? Actually, the numbers also means like the pixels, okay? So an image is made by pixels, right? If you guys are aware, RGB colors, right? So the pixels tells you the intensity of the color. So that's the convolutional layer, the one main important layer, which you would add up, right? 2D. Of course, there are many types. The other one is what we call the max pool that you saw in the diagram just now. So what is max pool, right? It basically takes the image and in a grid of 4, it just basically abstract away 20, all right? So that's basically maximum. You realize there's no weights to calculate, okay? You also reduce the complexity as you 4 by 4, you immediately make it 2 by 2, okay? So you also help to prevent the model from overfitting. The third layer will be sort of the dropout layer, right? Which is where the it randomly casts the neurons away, right? Okay. This layer is quite interesting. Okay. If you put a dropout layer, what it does is that it sort of tells the data that this is going to be 0 randomly, right? So there will be no data going forward. Can you see there's no weights, all is disappearing? But those that are able to pass through will be continuing, right? So at each episodes of learning, it starts to do this change, okay, in order to sort of also help to prevent overlearning, okay, but more importantly, also prioritize certain features at different learning phase. So these are 3 quite common layers that you will see, right, in most off-the-shelf codes that you find. They either have a convolutional layer, a pooling layer, or the dropout layer. A pooling layer can be not just max pool, it can be average pool. A dropout layer can be 0.2, 0.4 percentage of the neurons being dropped, depending how aggressive you want to forget the training data or you want to make it learn less, right? So those are some things you consider as you build a neural network, right? So what is that kernel that you saw was moving around, right? So in essence, if you can see the relationship of a kernel to an image is this, right? 1 can be sort of the most dark region of the image. 0 is basically sort of blank in reference, okay? So actually a kernel is almost like a filter, right? Or a coloring, right, that you put on the image itself and you multiply it to sort of change it. The only interesting thing is a lot of times the kernel weights is also learned by the model itself. So the model is actually learning the kernel weights, okay, rather than you telling the model what's the kernel. What you set to the model is more of the kernel size, right? Is it 2 by 2 or 3 by 3? That depends on how fast you want to shrink the image down, right? So that is some very key kernel filter of that features itself. Okay. Now, in essence, the CNN has hyperparameters, right? Which we have to take note, right? Especially in the convolution layer. So in the convolution layer just now, when you saw the kernel multiply with the key of the image, there's a few parameters, probably only covering mainly of 3. Okay, will be things like striding, right? Okay, which is such as how much you see the kernel being shifting, right? Okay, if you have, let me reset the slide, right, so that you can see, right, it's actually moving. Okay, how much is it moving per time? It's moving by 2 units, if you can tell. Okay, so the striding 1 will move 1 unit to the right, striding 2 will move 2 units to the right. So imagine if it was originally 7, 7, if each time you strike 1, right, at the end you will get 5 by 5, okay? 7 by 7, each time you strike 2, you get 3 by 3. Okay, so let's say 7 by 7, right? So 1, 2, 3, 4, 5, 6, 7, okay? So this is 1, 2, 3, 4, 5. Yeah. If I'm going to strike 2 by 2, so first I learn this, right? Then I'm going to move 2, I learn this. Then I move another 2, right? How many values am I calculating? 3, right? That's why I'm going to fit 3 in the end. Then if I continue also on the vertical side, it should be 3 by 3, if you can tell, right? So hence y7 by 7, strike of 2 again, 3 by 3. So how this 2 by 2 is basically from a 5 by 5, you strike by 2, okay, you will get 2 by 2. Now, why could this be important? Because intuitively, right, the strike will result in less data coming from the original image, right? You have less overlap if you can intuitively see the impact of that, right? Also means the features get lost much more, right? So sometimes when you have more strike, it's trying to just learn the main features in the image, okay, and drop. So all these, well, you cannot explain what's happening in a neural network as I explained just now, right? Every single steps have so much change. Intuitively, you can appreciate why striking affects the way it's being learned. Okay. The next kind of common parameters that we tune for the convolutional layer will be sort of padding, right? So if you can see, padding is basically you add a white color border to the boundaries, right? So why do you do that? Is because you want to increase the importance of the borders. So now you see uh, as you strike, right? If you strike, you increase your strike, you also increase your padding. The padding actually cancels out the striking. So in that essence, your image retains almost the same size as original. But the weightage that you have assigned due to the convolutional calculations of the matrix, right? As you saw just now, the borders now become much more important, right? So this is where there is an importance of that key of understanding this, right? Why do we pad? Okay, because we want to strengthen the weights of the borders. So image computer vision, though you cannot again understand what's happening in the weights calculations, right? Intuitively, you do see the impact of the uh, key of sort of changing all these parameters, right? How does it really affect the image in a more salient way, right? So that's something to think about as you train or even learn from a model that you can get, okay, or prototype for the deep learning problems. Okay. Now, next will be dilation, right? So dilation is where, interestingly, you split the global view. Okay, so this will be the last parameters to go through, just to give you a full breadth of the things that you change to affect the image, right? So what you see is that just now you see the kernels moving in very rectangular movement, right? Now is that you split the, can you see the darker region here, right? Correct? So these darker regions are basically split. You can dilate 2, you can dilate 3. So it sort of, again, intuitively give a very global view, right, of the data, right? So in a way, you are trying to learn this global view, but at the same time, also reduce the cost of learning data. Right? So hence, okay, that actually gives you that importance, right? Okay. Now, so hence, beyond the bespoke models, right, is where you can do things like transfer learning. So what's a transfer learning? So there has been various state-of-the-art models, right, that we can easily get from open source environment. So one first very early phase of CNN convolutional model for image recognition was AlexNet, right? So as mentioned, they use which is basically a reloop function, right? Okay, and this was stacked on another layer called LearnNet. All right, okay. Then after that, moving on to VGG16, right? So this one is where you stack on the AlexNet. So interestingly, what you can see is to build a deep learning model is literally playing a Lego, right? You take one with 8.1, you add 13, add few more layers, right? In exact terms of 5. To that, you get another better one, VGG so far, okay? With convolutional, as you mentioned, as shown just now, right? Okay, aggregating the features, max pooling the main highest pixel in the image. Okay, and finally, softmax is the final prediction, right, which is 0 to 1. Okay, what's the probability that this is a car? Okay, from 0 to 1 confidence. All right, so that is basically the key here, right? Okay, that you are trying to impact. So that's for VGG. Okay, and how do you take all these state of the art transfer learning models? Is that you download the weights of each model, okay, whether from PyTorch or from TensorFlow, okay, whichever package you are more familiar with, and then you decide whether you want to relearn, okay, or retrain the last few layers, right? So that's how you are deciding it. Okay, now one key thing is there are main problems solved by CNN. These are not the obviously this is not exhaustive, right? It's not like entire computer vision field is only these 4 problems, right? Image data, which is one of the main unstructured data you have, right? These are quite common. One is literally, like as mentioned, classifying image, right? Is this a cat? If you think that there's no business value knowing whether there's a cat, you can see whether is this a dense crowd. All right, if this is a dense crowd, you might need to know there's some control or patrol, right? Especially during COVID times, right? Other kinds that is slightly more advanced, right? So the difficulty increase, right? Is where object detection, as you saw right in the beginning of introduction, right? Is in the image, I'm trying to figure out every single object in this image. And it can even be different species of dot, right? Like red, green, blue boxes to box them up to show different species. Otherwise, from the satellite view, a cargo plane with 60% accuracy. These 3 are quite synonymous, okay? Object detection, semantic, segmentation, and instance are quite synonymous, right? The difference is that for instance, different from bounding box, right, is that instead of drawing one box around it, which will create a situation of do you accurately overlap it, right? It's just basically take the entire image and label with a red color masking, right? If you mask it, so shade it with all red, you are telling that it's one species of dog, right? Then each species is one color. Okay, if it's semantic, is that all the dots will still be in the same color. That's about it. Okay, so that's just a key difference. So usually this semantic is due for like finding a highway out of the boundaries, right? Whereas houses, each houses is of a different color, if you can tell. All right. Okay. Now the general process of CNN problems, right, is this. Okay, so you might want to really appreciate this because this is how you usually do a full pipeline. Right? So in real world, where you do any problems, okay, for any competition or in practice, right, you take the image data, you have to do image processing. Unfortunately, and fortunately, I'm not really covering image processing here. Why? Fortunately, it's also too much information already for you guys. Unfortunately, this is a very crucial step. Okay, so just take note of some examples, which is like, okay, changing the color, cropping, rotating, basically increasing image size also. Each time you process the image, you will increase the data size. But it's very important, right? Because there are many ways to get a cat image. A cat can be without a tail, but you can tell it's a cat, but a machine cannot, right? So you have to augment that image for the machine to learn. Okay, and extract all the features, right? Literally like any key contours, points, edges, right? Like padding just now. And finally, training. Training, there are always just 2 approaches, right? You build your own layers, and as what I've explained, all the activation function, layers, neurons, type of layers, hyperparameters, right? Striding, padding. Or you just download a pre-trained model and you do some adjustment from there, okay? So commonly, pre-trained model is quite the common approach for most competitions, right? On Kaggle, on famous competitions, and even a real-world practice. Because these models are already trained on a large set of corpus of data, so you just need to customize it and learn it on your own data. And last but not least, inference and predict incoming new images, right? Okay. And to sum it up, on the content per se for the theoretical part, is to give some key to how you should change the models to improve and your learning, right? So there are always 2 kinds. One is a model-centric approach, which traditionally has been very much advised. So it could be a full pipeline change, right? So what you can do is train a neural network to label the data. Imagine label image, right? You send a model, which is like a teacher, to train it. After you pseudo label it, you feed back into the neural network and you train a larger data set this time around after you augment the data. So the goal of this is to generalize outcomes, okay, and predict unseen data. Okay. Another approach is for model is really to, as mentioned, use data that is coming from pre-trained learning model, right? Like efficient net and also ResNet. So depending on training size, if from small to large size, small can be few thousand, medium can be 1,000 to 10,000, large can be beyond that, right? So you can see that if it's small, what you just need to do is download that pre-train, right? And this, you just need to retrain the last layer. So when we say freeze, right, it means that we don't really relearn the layers. Remember, every layer holds a weight, right? So neural network, after it learns, you store the weights as a file, right? As a memory, right? It frees the layers. You only train the final classification layer, right? Because you might be predicting 3 class this time around. But the pre-trained model was trained on thousands of images, right? So you need to probably want to relearn, especially the last layer. Okay, softmax is just 0 to 1, right? Okay, so that's the goal. If it's medium, you might then want to increase learning beyond the last few layers. Why, right? You want the model to be able to pick up more features from an image, okay, since you have more data as well. So you unfreeze the layers here. So this is unfreeze, right? Okay, you still freeze these layers. So these layers is still being freeze. So freeze means you don't train it, right? You basically drop all the weights of the new last few layers and relearn it with your data. Okay, if it's basically large new corpus and is significantly different from the corpus of the original model that has been trained on, which you should need to do some research, right? Then you will just retrain everything. So the goal of how you decide how much to retrain is simply this, right? Okay, if your data set size and data set similarity, right, as you can see, okay, is where if the size is big, you can train the whole layer, okay? But if the data set is quite similar as mentioned, right, it's not very different, you just need to train the last few layers, okay? This one is just the classifier, okay, layer. All right, okay. Otherwise, if it's very small size, okay, and it's so similar, right, also, you don't even need to relearn the model, you just need to train the classifier layer also. So most of the time, the classifier layer has to be retrained. Okay, the classifier layer is basically the last layer where you predict the outcome of your image, right? Is it a cat? Is it a dog? Is it a car? Whatever. Now, pre-training means, right, the models is already trained by, say, Google, Facebook, Amazon. Okay, there are many pre-trained neural network models. You can check Hugging Face for NLP. You can check all the convolutional layers models for computer vision. So what you do is that these models usually they have been trained on all the Google image, for example, or even Amazon e-commerce image, right? Which is very large, rich data set. They remember and store the weights. So what you can do is you download that model with the weights. You just have to do some adjustment. That's why it's called transfer learning. It means you transfer what you have learned on the data elsewhere of these big models. Fine tuning is actually what you did when I mentioned like striding, padding. All the hyperparameters you have, right? You have to change and tune it, like learning rate. That's how you fine tune the model, right? You have to customize the values. All right. Okay. So hope that answers. Other method is basically the data one, which is quite key. So as mentioned, commonly in computer vision, we found that if you have a data-centric approach, right, you will basically already have a 16.9% incremental compared to the model. So a lot of times data is the main source of ingredient, right? So check the labeling of data, etc., or even noisy data. Another way to prevent overfitting is how you train, right? So you have the original data, you cut the data into training and holding. Then finally, you have another hold out validation to test it. Okay, yeah, so someone shared the pre-trained models by Bihun, thanks a lot. So you can see cross-validation, right? So train, test, split, okay? So training is like you learn the martial arts, new martial arts yourself, right? Validation is you fight your sensei and see whether you have honed the skills. The real testing, which is the future that you have not seen, right, is where you go to the real battlefield. You either die or you survive, right? So that's it. One main problem of neural network is that you can really overfit. So there's another parameter you can set is early stopping, which means that as it trains, right, you just put a cut so that you prevent it from overlearning, right? So you stop it if there's not much incremental or the gap between the training and testing error are really increasing. So you don't want to go further. So this is your epoch, right? Basically your training cycles, you can stop it early. The beauty of neural network is this, unlike machine learning models, is that because it's like Lego, you stack up, right? Which means you can stop it, can remember the previous checkpoint, can restart learning from the previous checkpoint because the weights are learning very incrementally. All right, so that's the beauty of deep learning. Okay, otherwise it's the dropout that is key, right? Where we are looking at randomly forgetting the data along the way. All right, so that sums up probably a few key concepts of neural network. Any clarifications so far? Okay, if not, let's probably go through some samples, right? Okay. So this is just SageMaker. You can simply go here, right? I'll get the instance. All right. Let's do custom examples first, right? Okay, so let's play around with some custom example. So first, we want to train a classifier, okay, and in this case, an image classification problem. Okay, so CIFAR10 is a very common data set. It basically has a few key class, okay, like your airplane, bird, cat, any class you see, right? Of course, CIFAR10 is a shorter, smaller version. There's a CIFAR 100, a larger one. Okay, the image are usually 3 by 32 by 32. I hope you guys can see. If you feel that you need the larger, please just put it in chat or something like that, right? So Y3, right? Remember RGB, right? You have 3 channels, right? So that's 3 colors. Okay, so the vectors that you should see is basically 3 by 3, right? Okay, so yeah, so that should be how you should look at it. Okay, so in each image, three dimensions. All right, so that's it. If you want to analyze the image, you can get Pillow or OpenCV. That's quite common, or doing some transformation. Okay, and this guide will be using PyTorch mainly, so feel free to pick up on it if you are not familiar. Otherwise, the same version can be done on TensorFlow and Keras, right? So usually for PyTorch, you do have to put into a data set which is iterator, right, to loop the image, which then into a data loader. That's about it. Okay, so just a very quick brief introduction. So how do you usually train a classifier? Right? So there are a few steps that you do. So in this simple guide is basically normalize the data, right? Why normalize? Pixels is always 255, 255, 255, right? RGB, right? So this will be sort of white, right? Taking everything in. So you want the weightage of the image to be significantly equal to 0 to 1. So you just need to take 255, all the pixels divided by 255. Then it will always be between 0 to 1. So that's normalization. The goal is to help the model to learn faster. Okay, the pixel relative comparison is sort of still maintained, right? Because 255 versus 250, you divide to 1, it's basically like 1 and 0.9 something, right? So it's comparatively still similar. 255 is still larger than 250, even after you normalize. Okay, just that now the model doesn't have to compute a larger number, which takes up more time, right? Okay, and then the bespoke convolutional neural network. All right, so if you use, you can just change the kernel to PyTorch, right? All right. Otherwise, which is already in PyTorch. Otherwise, you have to install or clone the PyTorch library package. So if you imported it, right? Okay. So that's I wouldn't probably run everything because it might take a while. Okay, but since it's already run, so we can go through it. Okay. So first, after the image is coming in, right, you will realize that I want to set some transformations in the image. So in this case, I'm actually converting it to a tensor. So PyTorch and TensorFlow handles in a tensor format, which I am not going to elaborate. It's more on the data processing step, right? But that's basically, you have to prepare the data in that format. Okay. Yeah. Are you able to see right now? I don't. Okay. So, right, what you can see then is that after that I normalize, right? So this is another way of normalization also. It's basically dividing by the mean of the channels and the standard deviation of the channels, okay, to give it a normal distribution. The batch size here, you can change it, right? All these are parameters that can change. The augmentations you also can change, right? Here we are not doing very advanced flipping, cropping, or blurring or sharpening. If you want, you can figure out how to get the, just search on PyTorch standard syntax, right? Batch size is just 4 image per, then data set CIFAR tank, loading it. Okay, you download, shuffle the data, okay, and put into a data loader, okay, for the train and the test set. All right, so these are already downloaded and verified, right? Now, usually when you deal with computer vision problems, right, you might want to print out the image to see what's happening. So get a library, right, or PLH or even a OpenCV just to iter the image. So you can see basically it's 32 by 32, right? So it's more condensed. You can actually do a transform of the resizing, but that's fine if you don't want to do that as well. So just have to print out sheep, car, frog, and deer. So this is the image that you see. All right. Yeah. Now this is where what we cover comes into handy. So Torch has an abstract class of a superclass of neural network. Right? So this is NN, okay? So you have to import NN functions. Okay, so class net initiate it. If you use PyTorch, this should be the standard code template that you always will use, right? So what you do is self-initiate a convolutional layer, okay? Convolutional 2D, right? Taking 3 by 6 by 5, okay? Pooling layer, okay, max pool, okay. Remember what's max pool, right? Basically, if I have an image of 25, 20, 40, and 16, if I do a convolutional, the max will be 40, right? So if I big image, I reduce it drastically, okay. Then another convolutional 2D, okay, 6 by 16 by 5 again. Last but not least, the last few layers of the classifier is 60, right? Okay, so you realize that every layer leads to the next few layers in terms of the output of the previous layers impact the input of the next layer. Okay, and last but not least, this is the final one, which is fully connected tree. Right? FC stands for fully connected. Okay, so this one is 10. Why we have 10 classes, right? CIFAR 10. So this is all these are just you setting the layers. So you setting the layers, right? Okay. What happens next is, remember the forward passing of the data. So usually we push a forward of the data going forward. So any factor that comes in, right, which is the image tensors, okay, they come in. I will first do a convolutional layer of 2D, right? I activate based on the reload function, if you recall, right? Which is this, right? 0 to Z, max 0 to Z. Okay, and then I pull it, right? So that's the key, right? So pulling is to max pool. So initially in one line of code, I'm doing 3 things, right? I convolve the image, means I use a kernel to extract the features, right? Then I pass into activation and activate it. Okay, if it gets strong, it will have output, right? Then I pull the maximum of that area of that region, right? And that will be my X. Then this is the first layer, right? I feed into the next one. Okay, I convolve a second time, reload again, and then pull it again. All right. Then transform the shades to just to view it and do a fully connected. The last one is just a return for this vanilla one. Okay. Usually you might want to apply a softmax here as well, but that will be returned your final class, right? X. Okay. So the softmax should be applied here because this was relook. It's how you change the activation function might make incremental impact on the accuracy later on. All right, so that's the key of that. So every comma is telling you basically input, output, input, output, input, output. Correct? That's for linear layers. Convolutional 2D, remember you have 3 channels, right? So 3 by 6 by 5. All right. Okay. Now we covered loss function, right? So we want to reduce the loss. This is a classification problem. So for classification problem, the common loss criterion is actually cross entropy. Okay, there are others. Feel free to explore. So that's something that rather quite fixed. So you don't really change that. Okay, what you change is the optimizer. You can change from HGD to more advanced optimizer, which you can explore Adam W, whatever. Right. So all the parameters, okay, you are trying to. So net is the model, right? If you can tell, net was the model. Okay, you initiated the net, right? By this model, you started it. So you call the net parameters in. We covered just now again another parameters, which is learning rate, right? Okay. And so that affects how fast you update the weights. One thing we didn't really cover in the theoretical uh, content just now was the momentum. This is more for stochastic gradient descent, okay, parameter for it. So how much it learns fast, right? Okay, or change. Okay, that's the incremental momentum for learning. For epoch, basically two. This is running 2 rounds. So one thing about deep learning is you usually don't run like many rounds like random forest or your machine learning, right? Machine learning like logistic regression could iterate 1,000 times. That's 100 is the max, if I'm not wrong, like convergence iterations, right? But for deep learning, usually two to 5, you might see impact or not really. Okay, so there's no need to iterate so much because the layer is huge also, right? So set the running loss to calculate the loss. Here you are just using setting the inputs and the labels from the data in the loader, right? Then zero grade will just to sort of improve the gradient calculation, right? Usually for evaluation, you have no grades. It's basically to learn, do not change the weight, right? So you can calculate faster. Outputs is the, after the inputs of the data goes in, your net is your model again, right? If you recall, this is the model, right? Okay, this is your image, right? Okay, feed the image in the data, net will process the forward function just now you saw, come out with outputs and the labels will measure the loss function, right? Calculate the loss. Backward is where I backward propagate, which I explained, right? I learn forward, then I calculate backwards the weights again. Okay? And please do not annotate on my drawing. Yeah, thank you very much. Yeah. If you have questions, feel free to ask on the chat group. Okay? Then update the optimizer steps, right? Okay, so finally I print statistics. So basically, as the epoch 1 goes in, okay, and number of rounds, right? Okay, so this is my loss going down. So it's basically finished training. This is quite a lazy way to calculate. Actually, to be frank, you can do more analysis, right, and metrics. Remember that neural net, you can save the weights, right? So I actually save it into a CFA path, PTH file format that saves the weights, sort of the state of the dictionary of the parameters, right? Okay, so now is basically ground truth is cat, sheep, and the plane, right? Okay, so I'm just going to print it out, right? So you can see predicted for this is cat, car, and sheep. Okay, so it's not very accurate. Okay, so now you apply to the whole train test, the accuracy is only 50%. This is a very bespoke model, right? Okay, of 10,000 image. Okay, then finally, if you want to do more evaluation, as mentioned, you can do accuracy for every class. Or alternatively, if you recall from machine learning, you can do similarity or precision or recall. These evaluation metrics still hold true even for deep learning, which is why it's not covered here because it still holds true the same evaluation metrics. All right, so plane, car, birds, etc. So actually you can tell some image are doing better like car, okay, quite distinct. The worst is like cats. All the animals are pretty challenging for it to learn. Okay. Anyway, this is only a 2 convolutional layer, right? So there's only 2 convolutional layer here, right? Which is this first 2. The rest is just final calculations of the classification. So that is reason why probably this model is not that advanced, okay, for CFA 10 data. Of course, you can simply Google and find better results of that. All right, now any clarifications, feel free to key. Now, one thing is that, remember you are predicting 10 class, right? So 10 class means that 10 class will have probability. So for example, class 1 to 10, right? or ASEAN 0 to 9 due to Python. Regardless what is it, right? Each one will have a probability, okay? So a p-value, right? A probability. Touch max will get the one with the highest probability, okay, in the tensor, in the essence, right? So that's where you will predict the final label. All right, so that's one as well. I think one-hot encoding was also covered more or less in the machine learning session. So again, if you require to recap on that, why the image can be predicted as a number is because it has performed one-hot encoding already. So that is another key concept. All right. Now, if you will need to take a look at maybe object detection, right? Okay. Yeah. So just now was image classification. Okay, let's take a look at how we do object detection, right? Okay. So this is a very popular task in computer vision, right? Okay. So what you're trying to do is you're trying to predict boxes around objects present in the image, okay, and recognize the object itself. So there can be many objects in an image, right? Most common pre-trained model, so far, two most common one is faster RCNN and YOLO. Okay, this you can do more research on it. So let's say imagine this situation, right? I want to predict a road sign. So a road sign can be four kinds, right? Traffic light, a stopping sign, a speed limit, or the crosswalk. So these are all the key we are doing. Do take note that every object detection there are two phases actually. One is a regression, right? To find the coordinates of the box. It's an image, right? Okay. So this image you have x mean and the y mean on the top left, right? If you are following a COCO tools. Also, object detection have many annotators that you can use, right? YOLO has the annotators as well. So COCO, COCO is quite common. So you do need to set it up if you are interested. Then you have to regress the box, right, to be exact. So the red one is the predicted one, let's assume. The orange is the ground truth, all right? And then finally, after that, you classify into these four groups, okay? So you regress the box and classify. These are the package to install, okay? Data coming from Kaggle, okay? So you are building helper functions, right, to look through all the image, all right? So this is where the road sign image you are looking at, okay, that are coming in, okay? Then generate the annotation. So you can see in the generally every single file, right, has a width and a height of the image, the class of the image, okay, is it a speed limit or traffic lights or stop or crosswalk? These are the bounding box coordinate, right? So you can basically see that if x mean and y mean is here, so 117, okay, 116, right? This is 187, 116. Then this is no, this is 187, 116. Sorry, 166. Yeah, 166, right? And the y will be 235, right? Okay. And then this will be 187, 235, 117, 235. Okay, so that's basically the bounding boxes of that thing. The width and height is not the width and height of the box, it's the width and height of the image itself. All right. So all the boxes are different, if you can tell, okay? Just by the name. Okay, so encode the data, right? Okay. Resize it, okay, create a mask. So these are all general functions. So in essence, what are these functions trying to do? I'm trying to read the image. So using a CV2, open CV to sort of get the RGB of it. I'm going to create a mask, okay, for the bounding boxes of the same shape as the image, okay. Convert the mask into a bounding box. Remember instance segmentation where every color of the image is sort of colored, right? So that mask will be sort of converted into a bounding box. Okay, 0 will just be a blank label, right? A background which is not having any boxes. And then finally generate the array of the bounding box itself. So all the parameters, right? Okay. Now, resize the bounding box if you would like to do that, okay? Also populate the data, okay, with new of the bounding box that you have resized, right? Because you just done it. Okay, so let's say sample image, you're going to print it out, right? Read the image, create a bounding box, and the masking for it. So here is the box, right? If you create a gray mapping, it will be basically everything will be black background and then a gray location here. All right. So this is basically how you readjust the bounding box, resize the image, right? This was the original image, you are trying to resize it, okay, and to a size that you can compute. Okay, so you are doing some data augmentation here. All right. So first, the general pipeline is load the data, resize image. If you resize image, you have to resize the boxes, right? Makes sense, right? If the image gets larger, your boxes that covers the object has to increase proportionally the size, right? Okay, look through some sample image. Furthermore, do any augmentation you want, okay? So while I didn't cover this theoretically, generally you do it in your pipeline. So for example, you can do a random crop. A crop is basically like 80% cutting of the image, right? Okay. Then again, just print a sample image. One good practice in computer vision is each time you do a change to the data, you should print the image out. Otherwise, you will not really know what's happening to the image, right? Because you can't visualize in 2D, right? Then finally, data sets is the key main one that you put into the proper format for the model to learn. Finally is the model, training, and predictions. So the front part is where the heavy work can be also, or where you have to change the data and customize it. All right, so as you can see, I'm trying to understand like if this sign here, how does it look like? Mask it, the map is gray, okay, with a black background, right? I have actually resized it here, okay, with the new bounding boxes and the new path to the new data that I have resized. So each time I resize the image, I put in the new path, a new directory, right? Okay, so that's the goal I'm trying to resize using CV2, which is OpenCV package, okay, for image processing. Right, at this moment, you don't really need tensors yet. You don't really need PyTorch yet because you're just doing basic data cleansing, right? But you can also use PyTorch syntax to do it if you're interested. The label encoding is here, right? As mentioned, 0, 1, 2, and 3. Okay, so each class is basically a number. Okay, for that, all right. And that's basically a few key things to summarize for all the functions that you see. Okay, file list to look through directory. So do remember also as you are dealing with image, right? Every image is stored into a folder, right? So when you are processing, you are just transforming images. So you are dealing with unstructured data. It's not as straightforward with a tabular data. So that's something that you might want to take notes, okay? That you are doing, okay? Now, some augmentations in this example is cropping, also random cropping also, center cropping. We focus on the center and cut it. So a lot of times is taking the size of the image shape, pixel and cutting it. So these are our random uniform is basically calculating a probability to cut the data, right? Okay, rotating is one that we would like to do as well. So for example, an image, I rotate it to 45 degree or even 90 degree, right? Okay, so in order to create different, so imagine trying to capture a cat upside down. Sometimes your camera can flip, right? Or landscape to portrait kind of rotation also helps in learning. Okay, so these are the things we want to do. So all this flipping, random flipping, right? Okay, left, right of the image, okay, rotating. So basically transforming it. Okay. Whatever you do, you will realize the image resize, the bounding box will have to change. So one thing about object detection is that as you change the image, you will have to change the bounding box as well. All right, so that is a very key value. Okay, so as you can see, my box is all the way there at this moment. So if before I transform, right, can you see there's a red color box here? It's flying somewhere in the air. Okay, this is original image. Okay, so now that I retrain it, okay, after transformations, okay, my boxes is fixed into the right side and the right area. But this is still regression, right? I haven't really do classification. Okay, so data set is basically now I'm trying to normalize the features. Okay, again by the mean and the standard deviation of the image, create a loop data set for the PyTorch. Because it's PyTorch environment, you do have to initiate all the transformation functions, the path of the image, the boxes, the target values, right? The length of the data set. if you want to get a specific image of the entire data set, right, you want to select the path with the index for each image, the label of that index as well, transformation X and Y of that image, normalizing of it, which is shown here, okay, and then roll the print it out, right? Okay, so return both the image, the class, and the bounding box. All right. Step to the data set to a loader. A loader will have a batch size. Remember what's batch size, right? How many images you feed to the model each time. Shuffle the data as usual. This time is 64. If you reduce the value of this, you increase the learning of every single features. All right. Now the model here is ResNet, so it's already doing pre-training. Okay, so just now I show you a case where we do CIFAR-10 with image classification, where you build your own bespoke model. Now ResNet is building an object detection, which is using a pre-trained model. Of course, ResNet is shown here, but you can use more advanced, like 101, 50. Maybe these are also viable. All right, so if you just print out ResNet after you load it, right, there's a parameter called pre-train true, means you have to load the model with the weights, right? In essence, so as you can see, this already has been built not by you, right? By the people that have developed the ResNet. Okay, which is convolutional 2D is the first one. Okay, batch normalization of it. We loop max pooling. Okay, then another few sequential layers. Okay, of quite a repetition of the few stack, right? Convolutional batch normalization, reloop function again, convolutional, and then batch normalization again. So batch normalization is taking the data and normalizing, okay, in batches. So that's a few key things to take note. All right, so if you just print out, you kind of repeat all the way. Last but not least is the last one. Can you see the last one is input feature for the last layer is 512 after all that has changed, right? Why? Because the last second layer of the second last layer is 512. So you get into 512, right? And you're predicting how many class? 1,000, right? So ResNet 34 was trained for 1,000 kind of image class. Okay, with 1,000 bias is true means the entire model has set bias neurons. Okay, for the model. Okay, so here layers. Okay, I'm going to find ResNet okay, up to the first 8 layers, right? This 8, okay, the children. Okay, for every layer. Okay, and I'm going to initiate my own model. Okay, and add to that ResNet, right? So first, I will have ResNet models pre-trained true. I'm going to take the first 8 layers only for ResNet. Then I'm going to add sequential layers up to 6, okay, and then features 2 for 6 to 8, okay. So this is up to 8, right? Okay, which is 8 layers, right? Then up to 6 for the first 6 layer of the 8, then from 6 to 8 again, the features 2, right? Put a sequential block there. Last but not least, my final classifier is using a batch normalization of 512 features. And key important is that instead of 1,000, right, it's now 4. All right. So if you are lost, what you need to know, at least to keep yourself not from loss, is that you have to change the last one, right? The last one is this, right? We know that this layer is doing 1,000 features at the end, all right? And you are not doing 1,000 features, you are doing 4 signs, right? So if you are doing 4 signs, what can you do? You change the final layer to 4, right? So 1,000 become 4 now, right? So again, a forward function. So by now you should see how a neural network using PyTorch works, right? It's very repetitive. Initiate each layers, the description of it, do a feed forward network with X as the input. Okay, features 1, run it for the first 6 models, first 6 layers, sorry. Then feature 2, okay, from 6 to 8, okay. Then reloop function it, average pool it. So this time around it's not max pool, right? It's average pool. So it's sort of taking the average of it. Okay, and finally predict the last 4. All right, so that's the basically bounding boxes. So training, you will update the optimizers with a learning rate. So remember, optimizer does the gradient descent, right? Learning rate updates the weight. So you set the function here, set the function to train the data, right? So the model, the optimizer, the training data, the validation data, episodes in this time around is 10. You definitely can change this. Okay, C is a counter like 1,000, right? Okay. So This is where you just set the functions, okay, with every index, start the model by training, calculate the loss, okay, all are zeros, right? Because you need to start to count and add to the losses. Finally, for every image, the label and the boxes, okay, you make sure if you have CUDA like GPUs, you set it to CUDA versions, right? Cost entropy again, because it's multi-classification, right? Okay, this is basically target class, okay? And after that, you calculate the backward propagation again, optimizers, remember and store the stats, okay? Then you add the total loss, all right? Then print the training loss, validation loss, and validation accuracy. Every round of training, all right? So output the class, output the loss function of the class as well. Okay, so that is quite a standard replication. Of course, for object detection, you have to take note of the bounding boxes, not just the class. Why that underscore class is the class label, right? Remember, is it a traffic light, is it a stop? Y underscore BB is the bounding box of it. So this is the validation matrix, right? Just to validate on the validation data. Remember to fact check that you shouldn't overtrain, right? Okay, so if you print it out, right, you realize the train loss and the validation loss is dropping, then the accuracy is actually increasing. Now, you do see it's not always increasing, right? The thing about deep learning, as mentioned, it is blind, right? As it starts to learn and train the weights again, it can improve. After a certain episodes, it can decrease. So as the curve goes, right, your training error, if it's continuously decreasing, but your testing error starts to go up, okay, what you can do is you do a early stopping. All right, in this example, there isn't an early stopping sort of set, but it can be done. All right, so you update the optimizer, okay, and that now your validation accuracy actually is much higher, which is actually good, right? You want the predictions to be more able to generalize. So after you make predictions, okay, you just need to print out the image. You can see that it's slightly above. So what does it mean? You have to fine tune the accuracy further. All right, any clarification so far with the object detection? So the pipeline follows what has been covered in the explanation guide. The codes itself, you are creating tools. The models is just this straight code. Why is it so short and simple? It's because you use a ResNet 34. And in this case, you only use 8 layers. So any rationale for that? Not necessary, right? You can actually keep the order before. It's just an example to show you how I can take a model trained by someone else on 1,000 image and take the weights and use it for my customized problem. And because I only have 4 class and less images, I don't need 34 sites, such a large network like ResNet 34, right? I actually reduce it to 8 layers. So that's just my choice. So that's fine, right? Okay. Clarifications? Now, is it complicated? Yes. All right. So let's look at a tool, okay, which is recognition, right? So we are going to explore next is how recognition is done, right? So if you saw that, if you build your own bespoke sort of image classification and even object detection, what we're going through, it does require some experience. You can take any customized code and just adapt from the scripts. Otherwise, slightly no code and code based. So the way you can use recognition is using a script as well to run it. Alternatively, it's basically just used to console to do so, right? Recognition is built to do a few goals. Object detection, which I have already covered. Even facial recognition, slightly different. You are calculating every features on the image, right? And trying to look for similarities between images in order to detect this person in this image belongs to this image in the database. Okay, which is facial recognition. Okay, so that's essentially it. In recognition, there's a lot of other features, right? What we have not covered in the training of the models is a lot of data processing steps. So sometimes you need custom labels, okay? And there's a ground truth labeling for the tool that you can do augmented intelligence. Augmented intelligence means basically you take the tool and you have workers, like your real workers, okay, split up the labeling of the data, relabel the bounding box, improve the precision of the data, right? Doing all the data processing as mentioned. And last but not least, also available for image and video. So that's really how recognition is being built. So if you just take a quick look at it, right? Okay, so augmented AI is where you use it with a lot of other AI services. So recognition is just one of the AI services, right? So as mentioned in the original introduction, is deep learning is being used as a product, right? It can be packaged in the product itself. So you can basically use object detection. Okay, so in this case, you can see this is a person. Okay, this is skateboard, and you can always see accuracy, right, on the right. So this is how you do. So you can put a request, basically send an image in. Okay, imagine another image, then you will start to try to predict. Okay, city, town, urban. Now some of the labels are overlapping because many people can label classify the image under many. One image can actually means many categories. Right, fair enough. So you can just upload, right? So this is literally for a test case, right? So if you want to build and use the tool, you can definitely do that as well. Okay, there are other problems that you can do, image moderation, right? Okay, so for example, you can blur the client, okay, or even this one, right? So more no moderation label here. So female swimwear underwear revealing clothes 62%. So if it is, right, means what it means for this moderation is the image is sort of blur and covered. So that's basically how the console can work, right? Even things in like text and image, which is originally optical character recognition, can solve the problem. Of course, deep learning helps to make it more precise, right? So it's Monday, but keeps smiling. So you box up every word and then convert from image to text. So this is where you do two types of constructed data, right? Okay, and that's really a key of that. Of course, other interesting problems are like celebrity recognition. One thing is also video analysis. Okay, so you can process a video, and as it process, right, it tells you who are the people, what are the 9 objects, right? So this is basically something that you can play, right? Okay, then it changes and it tries to predict as it plays. Okay, so all the response, of course, you can download it into it. Okay, so upload a sample video of your own as well. Okay, so put a video, then you can definitely play with it. And these are all the no-code solution. Right? Custom label is basically the one where you have to start to measure an accurate labeling of the data, okay, unique to your own set of problems. So that is where you might want to check out how you can do that. Okay, set up data sets for it. Now, let's say if you are not going for that demonstration, right? How can I access it from a script? So let's look at one with object detection, right? Okay. So what we saw earlier was we built an object detection of a roadside, right? Basically based on a bespoke ResNet model on our own, right? With the functions of all your activations, we look optimizer, learning rate, etc. Okay, convolutional layers, right? Transfer learning, right? Take only 8 layers out of 34, right? Out of ResNet 34, right? So those are something that we are looking at, right? Here is where the key will be using a service, right? So initialize the notebook. Okay, so basically Photo 3 is usually the one you use for AWS by now, I hope, to access services, right? Which PH, which we already covered, image, right? How to draw it. Okay, set up a session. Okay, get the region. Client, this is recognition for this. Okay, so that will be it. Okay, let's just write. Okay, to see the image. Okay, so this is a car, right? So that's about it. I'm trying to detect. So if you are using a service, right, slightly different, right? You are not building a bespoke model per se. You are calling the tool to help to access it. So that's where you use recognition to detect the objects, right? So label response, detect the labels, okay? Pour the bucket and the image from there and try to predict that, right? Okay. Sometimes you use this tool, you might find that this tool is actually can be much accurate than your own training. Of course, you do not have any influence on the modeling per se. Right, so if you would like to have influence on the modeling, then you would have to do the, just now what we've shown, right? Your own development of your own model, okay? But you can understand that recognition runs on a deep learning model at the end of the day, at the back end, okay? So you just need to display the response, right? So you can see name of a car, the confidence is 99.7, it's just almost like object detection, okay? Then bounding box is basically the width and the height. The annotation of this is different from just now, right? Just now was x min, y min, x max and y max. Here just width, height, left, top. Okay, just a few parameters of the boxes. Okay, and there's another bounding box, right? There are two cars here, right? So that's about it. Okay, sometimes when you do object detection, right, it could come out with many boxes on the same image because of the way it do the regression, right? So you might want to do some post-diagnostic such as threshold of a certain filter of the box. If the confidence level of the box is not like 90%, you just drop it, okay? Something along that line, right? So next will be vehicle. Is also detected here, okay? The rest higher are quite blank, so nothing significant. Or even alloy wheel, car wheel, sports car. So again, I say one object can be labeled under many classification, especially if you use a tool as such a recognition, it has a database of so many labels, right? So you can detect unsafe objects as well, okay? But it may not be accurate. So this car is unsafe object. Alternatively, you also can detect video, right? Which just now we saw like Jeff Bezos speaking, right? With another guy. So that's where you have to pull the objects from the image itself. So build call a video here, access the bucket itself, okay, with a jot, get the label detection, sort by a time, right? Okay. Then once it's succeeded, you can print out what's happening in the image itself. There's a timestamp here because it's a video, right? So what I've shown in the bespoke codes that we've done just now, right? We didn't go so deep into video. It's all image, static image, right? If you do video, it's a similar concept, right? You just have to cut the videos into image, right? So every timestamp, there's an image that it has to detect. So 0 is the original start, 458. These could be in terms of seconds, right? So that's basically counter, right? So that's basically how you are looking through the video and getting the confidence for each. All right, I won't go so deep into the results, but more of how you access. So as you can see, only a few steps, right? Call recognition service, get a job, launch the job to predict the label. Okay, then at every milliseconds, in this case, not seconds, right? So milliseconds, there's a car confidence of 86. Okay, car confidence 99. The car could be moving, right? So after you frame cut the image by per milliseconds, each image has a car that detects it moving. All right, in the video. Okay, so that's the response. So get object detection, you remember it's a job that you call to predict the video image, right? So that's where confidence comes in. Okay, and counting it. Okay, you can show the video here if you run it, and then every object is another way of labeling in the HTML format. All right, so if you, it will take a while, but I don't think that's critical. Yeah, but I'm just going to run it. If we have a chance to see, we see. If we don't have a chance to see, then that's it for now, right? Okay, so that should be fine. Okay. So if the video start to load the image with a job, right, then get the response, wait for it to be successful, then see what happens next. All right, and we can print the video. Okay, next. So that is example, right? So in a video, I can box the person out, okay, and a camera, a safety net. Okay, if he violates anything, then a red color image here to show that it's not fully safety of the person. Okay, okay. So that's the key. Okay, so that should be key. All right, so that should be a key here. Where's the video just now? Yeah. So you can see it's like even human belt driving, it can detect, right? So that goes in the video per se every single millisecond. There can be too many noise in the tool. So read up the documentation how you can filter in these 15 seconds. Okay, so to filter off a lot of like machine, etc. They are not so confident, like those 60%. All right, so that's one way you can do so. Okay, and then get back the bounding boxes. Okay, and finally, in the video you can do detections. There are other kinds of solutions with recognition, right? As mentioned, with a code-driven approach. Okay. All right, so that's some things that you can play with. Okay, I would like to close it off with a final, most advanced object detection model that you can try, which is what we call faster RCNN in this case. Okay, which is a two-stage model so that you can see how you can detect it. So first install your Coco directory siphoned. Okay, same thing again, set the data set. Remember length, get the image, number of image, right? Get item. For each item, what are the boxes? The labels of each boxes. Is this a person or not? Image ID for each. These data sets come from University of Penn together with Fudan. It's just to detect humans. So if you look the data, right, it's basically a walking human. Can you see? Now the power of object detection is this, right? There can be two humans, but because they are walking at different distance, the boxes are different. So it must be able to regress the actual boxes covering the human at the same time due to the different size of the proportionate people. Right? Okay. So same thing, set the data set, right? Transformations that you have, image and a mask, get the data, convert to RGB. Okay. Your bounding boxes, if it's Coco, you have minimum, maximum, minimum, maximum. As you saw just now in the recognition, you don't really have that. Okay. That was in terms of height and width and left and top, right? Okay, so that is one image. Now a bit about how faster RCNN works, right? In brief, so we are going to sort of have this area of image that you're trying to detect. You propose this region, it passes through your CNN, then it does a softmax to predict the class, right? It also in parallel try to regress the box. Okay, so that is a more advanced way of doing in terms of matching accuracy. So there are always fine tuning from a pre-trained model, right? What was the question on it was you take the model in, you change the parameters, right? You change the number of class, you could change the head of it, right? Okay. Otherwise, you also change the backbone instead of using a ResNet 34, you can use ResNet 50, for example. All right. So otherwise, the region of interest. Remember the confidence that you allow. So those are something that we want to filter off. Okay. So after you get the faster RCNN ResNet with the feature pyramid network, in essence, a pre-trained model. Okay, then you set the model, right? You just have to start learning in a learning rate of 0.05, gain momentum 0.9, stochastic gradient descent as the optimizer. Here we are learning with a dynamic rate. Why? We reduce the learning rate. Remember, high learning rate means you learn fast, but you are unable to get to the lowest point, right? If you learn to slow it down afterwards, you actually have a higher chance to get to the lowest point. Train for 10 episodes each time you see. This is a more, compared to just now, right? What you see now is that the accuracy of this is much clearer. Okay, the precisions for all the boxes, 60%. Okay, for small and medium, large kind of area size, the accuracy is different. So it's like how all the classes of label, what's the different accuracy for that, right? Okay, and finally, just do a prediction and test it, right? That should be so what is impressive is you see that this is quite easy detection, right? Can you see that there's also a detection at the back here, there's a human, right? So it's actually a pretty robust and rational, okay, reasonable. So that is again, just image out the predictions, okay, prediction, draw the boxes, okay, image, permutate it, box rectangle is box out, right? And that should complete if you need a more advanced model for object detections, just a use case for computer vision. And that should close out. Hopefully, that completes the content for today. And any questions, feel free to raise in the last few minutes, leaving it for Q&A. All right.
Thank Thank you, Instructor Solomon. Do we have any questions for the instructor? Maybe we'll just wait for a couple of minutes.
Yeah, so no worries. So hope that everyone got the introduction to your CNN series, image classification and object detection, just two main use cases for it. Okay.
And don't forget, we still have session number 2 tomorrow afternoon.